Okay, so thank you everyone for coming and the organizers as well. So I'm going to talk about droplets and isotropic turbulence, and in particular I'm going to focus on what are the deformation and breakup statistics of such drops, and as we go along I'll try to sort of describe the model more carefully. I should sort of point out that this is work done with my collaborator and friend Dario Vincenzi from the University of Nice. Okay, so to begin, to set the stage, what we are really interested in are small droplets. So, and the sort of dispersion, deformation, breakup of these immiscible drops are an important problem, and as you can see from these references, they have sort of wide application, especially in fields such as chemical engineering. And one of the things which sort of came up in the last few years is that the emulsion process itself sort of benefits from even a description of how a single droplet breaks up before you consider interacting droplets. So the aim of this talk is rather simple. It is to sort of look at such droplets which are sufficiently small, and I'll explain what I mean by sufficiently small in a bit, and to try and understand what happens in terms of deformation and breakup of these sort of monodispersed suspensions of droplets in a turbulent flow in time. And our approach would be, and towards the end, I'll discuss this a little if we have time, will be to sort of perform direct numerical simulations of a model which is not the best model to describe the whole physics, but which is good enough, A, to do direct numerical simulations, and B, to allow some analytical calculations. And I will sort of try and marry the two things together. So just to sort of keep everything in mind, since it's a short talk, the control parameters in this problem are the initial shape of my droplet. So think about ellipsoids, and then I'll sort of discuss how I can make them more elongated or less elongated. The capillary number, which sort of will tell you a little bit about how these droplets would try to relax to their equilibrium sort of shape, and the viscosity ratio between the fluid of the droplet and the advecting flow. The caveats that let me flag, instead of putting this at the end in the conclusions, are A, we are not considering secondary breakups. So to that extent, the model only captures up to the first breakup of a single drop. The breakup criterion, which I'll describe, is arbitrary, but we'll play along with this criterion and see that for the purpose of this talk, it doesn't change the picture much. And lastly, I will ignore droplet inertia. So I will consider these, the center of mass of these droplets to be just like tracer particles and move with the flow. All right, so that's the caveat that I should sort of highlight at the very beginning. And I should again sort of comment that we are really talking about small drops where the fluid velocity across the drop can just be obtained by a Taylor expansion in terms of del u dot r. Okay, so for people who are thinking in terms of more familiar work, which has to do with Hinz and Kolmogorov's results, those are really for large droplets. Okay, these are sort of sub-dissipative scale droplets. Okay, so with that in mind, let me sort of just to, even if we don't go into the details of the equation, just to sort of tell you that it was shown some years ago that if you write down the inertia tensor of these droplets, then it's possible to write a Lagrangian evolution equation of such a droplet. So these parameters, I won't sort of go through the details of this equation, but we can come back later. The key feature is that these droplets are being advected by a flow. So we've taken two approaches. For our analytical results, we've considered flows where we've assumed the velocity gradients, which are really the guides which are sort of pushing and deforming the droplets, to be to have Gaussian statistics and really delta correlated in time. And that allows us, and I won't go through the analytical results, but just flash the predictions from it, that essentially allows us to write down the PDF of the droplet sizes, which sort of satisfies the Fokker-Planck equation, which we can then go ahead and solve. And so the relevant references from where our starting point are here. The other case that we've considered is we've considered a real fluid turbulence. So we've immersed these droplets in a turbulent flow, and then we are going to study evolve in time and see how the droplets break or not. Okay? So the thing that one has to keep in mind is that the size of droplet essentially will be given by the eigenvalues of this matrix M. So you can look at the largest eigenvalue and the smallest eigenvalue, for example, and you can impose an arbitrary breakup criterion such that this ratio, the minute this ratio crosses a certain threshold, which just for reference is something of the order of 10 power 6, 10 power 7, you say that your droplet has broken. So there are no actual breakups which are happening, but we are sort of tracking how the moment of inertia tensor is evolving in the flow. Okay, so in the last sort of 5 minutes, having set up the model, let's sort of look at some of these results. So the first thing that one sort of plots, because that's the thing that we are interested in, is how to, what does the sort of time-integrated PDF of these droplet sizes look like? So here for different capillary numbers, and as you see, when the capillary number is rather large, you get a reasonable scaling, and these are the same things but plotted in slightly different ways, which I won't sort of describe. So if you focus on this graph, you, for example, see a very nice -1 power law emerging. So the analytical approach, where we sort of neglect Navier-Stokes velocity field, but just think in terms of velocity fields whose gradients are Gaussian and delta correlated, that approach allows us actually to predict the shape of these PDFs. And the analytical results sort of seem to agree well with what's going on in actual turbulent suspensions. What's rather interesting is that if you actually look at the probability of the PDF of the droplet sizes at different times, you can't wait very long because all the droplets would have broken, but at intermediate times where you have still a reasonable fraction of droplets which survive, you do see that although these PDFs tend to reach an asymptotic shape, it's very hard to detect any power law. And this power law really emerges when you integrate, when you are looking at the time-integrated version of this PDF. And this is something which sort of comes out rather more clearly when you're looking at the model flows where you see this picture emerge. I sort of talked about the fact that one can take initial distributions with different shapes. That is, you initialize your moment of inertia tensor, the matrix, with different elements with eigenvalues such that the shape could be anything you want. I should stress that this model maintains the volume of the droplet. So the volume of the droplet does not change under evolution. That's sort of imposed by hand. So now, for example, if you calculate the same object where I look at different shapes, so these 3 or 4 graphs correspond to different shapes or different sort of level of skewness of these drops. So one is sort of spherical and 1000 is really stretched out. Then you see that although this this sort of R-1 scaling persists, but for droplets which are really large, so for example, droplets which have the matrix has an eigenvalue of 1000, let's say, and so the initial droplet size is sitting here, you see the emergence of a secondary power law to the left of this. And the dominance -1 scaling is really seen beyond the initial droplet size. All right, and there is also sort of a dependence on the viscosity ratios, which I won't sort of discuss right now. The other question, of course, one asks, and especially if one is doing experiments, is what is the fraction of droplets which survive in time? All right. So, for example, you start with n droplets, and in our simulations, n was 1 million or so, and then in time you ask the question, how many, what's the fraction of droplets which have still survived? All right. So our model sort of predicts that this fraction should be an exponential in time. And the simulations, at least for capillary numbers which are reasonable, does show this sort of exponential behavior rather clearly. But what's interesting is that for beyond a certain threshold capillary number, the critical capillary number as it were, this decay rate, so the log decrement of this graph, really increases rapidly and saturates. Now, if you sort of try to measure the same quantity, but as a function of the viscosity ratio, so if you have drops in a fluid such that the viscosity contrast is much higher, you see that this decay rate goes down. So what it's suggesting is that if you have two very dissimilar sort of fluids, a minority phase which has a viscosity very different from the ambient flow, then those droplets take much longer and longer to actually break up. All right. So lastly, I'm going to sort of try to show you what is the mean lifetime of each droplet. So you start with a large number of droplets, and you actually keep track of how long each of these droplets survive, right? So we talked about the critical capillary number, and this sort of measure shows something rather strange, and that's sort of entirely consistent with our analytical prediction, is that for capillary numbers which are smaller than the critical capillary number, and at least I don't have a very good intuitive or physical understanding of why this is so, but that's what our theory and our numerics suggest, is that you have a power law in the mean lifetime of these droplets. However, if you're looking at droplets which have a capillary number larger than the critical capillary number, you get a logarithmic sort of decay. So the mean lifetime essentially goes down as log 1 over the initial size. So the basic message is that if you have a large size droplet, then the lifetime of this sort of starts going down. All right, so with that, and I'm at the end of my time, let me sort of make some concluding remarks just to summarize what we've done. So what we've essentially done is taken a very simple model of a single droplet which has Lagrangian evolution, all right? We've neglected inertia, and we've considered drops which are smaller than the so-called Kolmogorov or dissipative scale in the problem. And we've shown that the probability, the PDF of the droplet sizes show power law behaviors which are different depending on what capillary numbers you have, high or large. The number of surviving droplets, as well as the mean lifetime of droplets, show very good scaling and functional forms where the results from numerical simulations of homogeneous isotropic turbulence agree well with model flows. And finally, just as a perspective, right now with colleagues, we are trying to extend this approach beyond droplets to more extended objects such as dumbbells or bead models, where we would like to sort of see the breakup of chains of dumbbells in homogeneous isotropic turbulence. So with that, I'll end. Thank you.
Any questions?
Yes. Oh, so that's how we set. So the way okay, let me just go. So here, the way we set up, or rather, Maffetone and Minale set up is that we define the symmetric positive definite tensor where so if you consider an ellipsoid and you look at its semi-axis and the square of the semi-axis, so this inertia tensor is set up in such a way that the eigenvalues are really the square values of the semi-axis, and the eigenvectors are its directions. So this can be worked out from the moment of inertia tensor. It's sort of messy, but yeah.
If no more questions, then let's thank the speaker. So.